Well, greetings everyone. It's time for another amplifier comparison video. What I'm going to do is test the TDA7294 amplifier on the Quantasylum. So I'll compare the board I made with this TDA7293 board, and when I'm done with that, I'll pull that chip off this board and put in a 7294 chip, and I'll compare that. So 3 comparisons. Now you can't just pop a 7294 on a 93 board because the bootstrap loader cap goes to a different pin. So I'll have to make that adjustment. And I'll need to change a resistor value so the gain's the same on my board. In the feedback divider network, I used a 1K ohm resistor, and they're using a 680 on this board. So I want the gain to be the same. So yeah, curious how this board will compare to the one I made. I expect pretty similar results, but we shall see. So I'll have to get the Quantasylum working. I have a new computer, well, an upgraded computer. I got parts and made pretty much a new computer out of it. I got Windows 11 on there. My old computer will be a Linux machine. Linux Mint XFCE. And I haven't tried the Quantasylum out yet. It should work just fine. Everything else has worked just fine, so stay tuned for that. And as I said in the other video, no more mid-roll ads. You know, when I'm watching YouTube, I hate when you're watching something and an ad pops in. Yeah, to make some money, I have to put the ads up in the beginning and end, but you know, I'll take a hit taking out the mid-roll ads, but I think it'll make the videos more watchable and enjoyable, I suppose. Okay, I got the 680 ohm resistor installed, making sure it connected to the right position. I can't believe it. In the last video, I had the lead one position over, and the amplifier would just oscillate. I didn't see it. I was going crazy trying to figure out what the problem was. It was just a mistake. So now I have it powered up and nothing. No oscillation. Good. So we can hook it up to the Quantasylum and begin testing. So I'm going to test my board first. And I can't assume everybody watches my video, so I'll have to show everything. So we have the power supply running at its max voltage, plus or minus 32 volts. That's my non-inductive resistor bank, switchable between 4 and 8 ohms. The board here, I use these large caps here coming off the supply. And the Quantasylum audio analyzer. Okay, plug the Quantasylum analyzer in with the latest version of its app, and everything's working just fine here under Windows 11. So what I do is my kickoff test, 1 kilohertz, 1 watt at 8 ohms, just to kind of get a baseline here. And look at that, 0.003%. That is excellent. Gain of the amplifier is around 30 dB. You can see we have pretty low noise. A little bit of 60 hertz electrical noise getting in. Dominant harmonic is the second. And these spikes at the real high frequencies, I think that's just noise getting in from outside sources. But yeah, we're looking at a very good performance so far. So let's move ahead. Frequency response. At 20 hertz, we're down a little less than 1 dB. That's because of the input capacitor value I used. I used a 1 microfarad when you really should be using a 2.2. I didn't want to use my more expensive film caps on this test board. And I think they used the 1 microfarad on that kit board as well, so I wanted to keep it the same. But if you wanted a flatter response out to 20, just use a larger cap, like a 2.2 or a 3.3 or something like that. At 20 kilohertz, it's less than 1/10 of a dB down, so no issue there. Okay, now I put the kit board in there, and it's a TDA7294. We'll see how that performs. Okay, the TDA7294 on the kit board, we're actually minus 1.8 dB at 20 hertz. So it's a little more than my board. It could be the feedback capacitor value. They have a smaller one. I think the input capacitor value is the same. But yeah, it's rolling off a little more. Again, it's all has to do with the capacitors. At 20 kilohertz, it's the same, just barely any roll off. Okay, I got the chip out of there. Still got to clean the holes out, but I had to sacrifice it. So I added flux to my desoldering braid to help me out. It really pulls the solder out, but those those double-sided boards with those vias, you just can't get all the solder out of there. So I had to take the pins out individually. I don't have the tools or the technique to get a whole chip out at once on these double-sided boards. Okay, so now I'll have to clean those holes out. I'll probably have to add solder on there and then resuck it back out. Hopefully it clears them out, or stick a piece of wire through it and heat it up. Then I'll get the 7294 chip put on this board, and I'll have to I took out the bootstrap capacitor because that has to be wired up differently, because the 7293 has that bootstrap loader pin it connects to. Well, that was nightmare fuel. That chip would not go in there. I had to take a piece of copper wire at the right size, heat it with the iron, and run it up and down each hole until I cleared enough solder out, because even just using the wick didn't get enough out. But I got it in. Screw it, I'm not going to clean the flux off. Then I had to modify this bootstrap capacitor. I had to go from pin 6 to pin 14 instead of pin 6 to 12. So I disconnected this hole and ran the lead to the capacitor to the output node here. So I scraped some varnish off the board, resist or whatever you call it, and solder that lead of the capacitor over to that point, leaving that hole is open now. So now it's connected from the bootstrap pin to the output, ground towards the output like it's supposed to be on the schematic. So should be ready to go. I even melted the corner of that capacitor there and burnt one of my fingers. Anyhow, see, this damn thing works. Okay, the 7294 chip is in the kit board that had the 7293, and if you notice, the response of the 7294 is the exact same as the 7293 on that board, because the capacitors are the exact same value. Same up here at 20 kilohertz as well. Results are in. Have some power versus distortion graphs here. The one on top labeled DIY, well, that's the perf board one I assembled, soldered together. And the one labeled kit, of course, is that soldered together kit that somebody sent me years ago. I will say, first of all, that I'm limited with my power supply, that I can only go up to plus or minus 32 volts. And that's what I used with the blue 8 ohm line. And I I don't recommend operating these chips higher than 28 volts, plus minus 28 volts, due to the current and thermal limitations, and that'll be the red line. So starting off here, look at this. Look how low that distortion is. For some reason, it's probably within measuring tolerance, but it looks like the DIY board distortion is ever so slightly less, but I don't know if it really makes much difference. It's so close. And see how nice and flat that is, from a few milliwatts to around 10 watts. And for some reason the kit board even stretches out more. It starts to curve up as well, but not as much. I'm not sure if that's the layout issue or the capacitors used, but I actually use larger electrolytic bypass caps along with the small value ceramics. And it could even be differences in chips. The datasheet shows minimum, normal, and maximum values, or normal, what they consider typical. So yeah, you can get variances between different chips. That's normal. But yeah, I do like what I'm seeing. Extremely low distortion throughout much of the power band. 4 ohms is a bit higher. Looks like it's around the 0.008 line here. This one's actually looks slightly lower, 0.007. Again, nothing that would make a lot of difference. And you can see where we knee up into clipping, and we cross the 0.1 line here. Both lines are in the upper 50 watt range, maybe 58, 59 watts, DIY board. And there's some divergence here at 1%. We're around 61 watts, 8 ohms, and a little over 70 watts, 4 ohms. Now what's interesting here on the kit board, about the same. Upper 50 watt range looks around 58, 59 watts. But the 4 ohm line is a bit higher, around 61 watts. And at 1%, the kit board is 63 watts, 8 ohms, and probably 73 watts at 4 ohms. So yeah, pretty similar results between the boards here. The main difference here is this, we start to angle up into higher distortion with this board, while this one's staying more flat before it knees into clipping. Okay, so now I switch the bottom graph to the 7293, and well, it's no surprise, it's virtually the same as the 7294. They're really the same chips. Like I said, there's some different pins on the 93 that give it some extra functionality if you want that. Okay, so now we're looking at frequency versus distortion. And I made a boo-boo on this one. I apologize. On the bottom graph, I like to normally use red for 4 ohms, but somehow I got them reversed. I use red at the 8 ohms, so just keep that in mind on this one. But anyhow, on the DIY board, kind of interesting results. The 4 ohm load drops below 8 for a little bit anyway, and it increases up to 20 kilohertz and stays shy of the 0.1 marker here. At 4 ohms it's around 0.07, 8 ohms is 0.05, and at 20 hertz we're peaking just a bit above the 0.01 line at 4 ohms, and we're well under at 8. Now with the 7294 on the kit board, our 4 ohm line is going ever so slightly above 0.1, and it's pretty much the same at 20. At 8 ohms we're bottoming out right at the 0.001 line. But what's interesting with these chips, their lowest distortion point is around 100 hertz. Usually I'm seeing amplifiers having lower distortion around 1 kilohertz, or at least in a broad range around there. So because of that, we're going above the 0.01 line sooner, around 2.5 kilohertz, 8 ohms, and a little over 1 at 4, ending up a little over 0.1. So interesting, the DIY board didn't quite get down to the 0.001 line, but at the higher end of the spectrum it stayed shy of the 0.1 line. Now with the 7293 on the kit board, it's almost a carbon copy of the 7294 within measuring tolerances. Okay, before I wrap this video up, I want to leave you with a schematic showing the recommended circuit for the TDA7294. I'm not really happy with the one in the datasheet. I think they skimp on component values, leave some important stability parts out. Because the bean counter that looks at the datasheet will see smaller components or less components, say, oh, this is nice for application, but I don't agree. I think leaving parts out is not a very good idea. So we'll start at the input. They have a 470 nanofarad cap on the datasheet. It's ridiculous. That's not going to give you a hi-fi flat response down to 20 hertz. I recommend increasing that to 2.2 microfarad film cap there. Also recommend having a low-pass filter that blocks RF and some oscillation issues on the input. For example, if the input's open, you have an RCA jack and you plug a connector in with the amplifier on, well, a fault of the RCA type jack is that the live center conductor makes contact first and you'll get a loud burst of hum. The amplifier could even feed back on itself and oscillate, and that will potentially damage the chip. So I recommend having a low pass filter to help prevent that oscillation. The next thing I did is I'm not using mute or standby, so you can just tie those to the V+ pin. If you want to use those features, refer to the data sheet on the circuitry for that. In the feedback circuit here, I recommend using at least 100 microfarad capacitor. They use a 22. Probably because they use such a low value on the input, they figured, well, we can use a smaller value here. Don't recommend that if you want better bass response and lower distortion at lower frequencies. I'd go with at least 100 microfarad here. Input bypassing, I recommend XR7 type ceramic caps. They have very low ESR and also low ESR electrolytics. When I was tinkering around with trying to get my breadboarded TDA7294 circuit working, just having the ceramics alone, the capacitive reactance at 1 megahertz is not low enough to remove some of the noise on the supply rail. So having electrolytics is important, and having low ESR versions is even better. So I'd recommend that. Finally is the output network stability components. They say you can do without any of this stuff on the chip. However, my testing shows that's not necessarily true. You really should have the output coil and parallel resistor. So if the amp happens to derive any capacitive load, it's not going to break out into oscillation. Amplifiers do not like driving pure capacitive loads, such as a long run of speaker wire. It reduces its phase margin and it could make it oscillate. So having that coil is important. And you saw when we did the square wave test, at certain voltage levels we were getting a little bit of oscillation on the negative side of the amplifier. And the Bouguereau cell here, I would still have that. I'd always recommend having that in the circuit. Now, operating voltages for the amplifier, if you really want to push it, you can run it at 8 ohms plus minus 40 volts, 4 ohms plus minus 28. But if you want to be more conservative, I would go with plus minus 35 volts, 8 ohms, and 25 volts with 4 ohm loads. So there you go, a look at the TDA7294 amplifier IC on two different boards. What I would consider an excellent linear audio amplifier. Also compared it to the 7293, which is really the same thing. Unfortunately, I had to cut it off the board to get the 7294 on. I will announce funeral services and viewing. Please sign the guest list. But it didn't make it. Too bad. Well, that's it for this one. Thanks for watching.